To process millions of events per second without dropping a single byte, a system cannot spend time modifying what has already happened. It must simply record, relentlessly, moving only forward. This split screen illustrates the architectural divide. On the left, a traditional message broker treats data as a checklist of ephemeral tasks, deleting messages once they are read. On the right, Kafka treats data as an immutable historical record. The data stacks indefinitely, and the consumer simply advances a read pointer down the list. Because this append-only log maps directly to contiguous block writes on a physical disk cylinder, Kafka bypasses the overhead of tracking state in memory. Sequential disk writes are fast and predictable. This decoupling of the data from the consumer's position in the log means multiple independent consumers can read the exact same dataset simultaneously, at different speeds, without lot contention. To understand how this works in production, we will construct Kafka from the ground up, starting with a single physical file, scaling out to clustered partitions, layering on horizontal consumer groups, and finally resolving distributed metadata with the KRaft consensus protocol. This shift toward treating data as history allows Kafka to scale horizontally, where traditional brokers often bottleneck. At the physical layer, a Kafka partition is a directory on the broker's file system. To prevent this directory from growing into a single, unmanageable file, Kafka splits it into log segments. Incoming data fills an active log file until it hits a threshold, typically 1 GB. Once full, the file rolls over, is sealed, and a new active segment begins. Zooming into a single log segment, we can see how data is retrieved. A logical offset integer passes through a sparse .index file, which maps that number to a precise physical byte address within the raw .log payload. A third file, the time index, maps timestamps to those exact same offsets. Only the single active segment accepts new writes. Once a segment is sealed, it is strictly immutable. Because older segments cannot be modified, Kafka manages long-term storage by dropping entire sealed files from the disk once they exceed a time or size limit. This is the default deletion retention policy. But for datasets like user profiles or state materializations, Kafka uses log compaction. As this cleaner thread shows, the broker scans sealed segments, identifies duplicate keys, deletes the older versions, and collapses the remaining blocks. Only the latest value for any given key survives. To comply with data deletion mandates, developers write a tombstone, a record containing the target key but a null payload. This null block instructs the cleaner thread to permanently remove all prior instances of that key from the disk. By managing disk I/O through append-only active segments and sparse indexes, the time it takes to read or write a message remains constant, regardless of the total size of the dataset. While a topic is just a logical grouping of data, the physical partition is the absolute unit of parallelism. Scaling throughput requires spreading these partitions across multiple brokers. The Kafka broker does not decide which data goes to which partition. The producer dictates the routing logic before the network request is ever sent. If a payload has no key, the producer defaults to a sticky batching strategy, filling a batch for one partition before moving to the next. This maximizes compression efficiency and network throughput. If the payload has a key, the logic changes. In this diagram, the producer passes a string key through a murmur-to hash algorithm. The resulting integer routes the data block to one specific partition. This hashing ensures that all the events sharing the same key, like the payment history for a specific customer, always land in the same partition, keeping the chronological order intact for that entity. To ensure fault tolerance, partitions are replicated. In this setup, every partition has one leader and multiple followers. The producer sends its data block exclusively to the leader, which handles 100% of the read and write I/O for that partition. The leader does not push data to its backups. Instead, the follower partitions proactively issue fetch requests to pull the data, replicating the log independently. This horizontal line is the high watermark, the offset point where all in-sync replicas have confirmed the write. The line remains frozen until both followers send their confirmation, then moves to encompass the new replicated block. To prevent applications from accessing data that could be lost in a failover, Kafka prohibits consumers from reading any records located past that high watermark. Separating primary I/O from asynchronous follower replication allows for high durability without locking the active write thread. Just as partitions determine storage parallelism, consumer groups determine processing parallelism. Because a partition can only be assigned to one consumer in a group at a time, the partition count is the absolute ceiling on your processing speed. If you deploy a group with 5 instances to process a topic that only has 4 partitions, 4 instances will work and the 5th will sit idle. As these consumers process data, they track their exact position in the log by committing their offsets. Here, the consumer reads a payload and then executes a secondary write operation. It appends its group ID and exact offset integer into a specialized topic called _consumer offsets. To manage this coordination, a designated broker acts as the group coordinator, monitoring the health of the consumers through continuous network heartbeats. If a consumer crashes, the heartbeats stop. The group coordinator detects the failure, removes the instance, and triggers a rebalance to reassign its partitions to surviving members. This previously triggered an eager rebalance, where every partition was revoked from every consumer, halting all processing before issuing new assignments. Modern Kafka utilizes the cooperative sticky protocol instead. When a node drops offline, this animation shows how the coordinator reassigns only the partitions orphaned by the dead node. The rest of the group continues processing without interruption. Storing state as just another append-only topic prevents the brokers from becoming bottlenecks during massive horizontal scaling events. Traditionally, Kafka relied on Apache Zookeeper to manage cluster metadata, leader elections, and broker registrations. As clusters grew, this push-based model reached a practical limit. Metadata updates sent to hundreds of brokers created significant latency spikes during failovers. In Kafka 4.0, Zookeeper was completely removed and replaced by an internal consensus protocol known as Craft. Craft treats cluster metadata exactly like user data. In this diagram, a dedicated quorum of controller nodes appends state change events into a specialized log called _cluster metadata. Rather than waiting for pushes, brokers now independently issue standard fetch requests to the metadata log. They pull the latest updates sequentially, achieving highly efficient eventual consistency. Consolidating the control plane into a standard Kafka topic reduces controller failover times from multiple seconds down to a few milliseconds. The architecture of modern Kafka is remarkably uniform. User payload data, consumer read state offsets, and cluster metadata are all managed using the same append-only log structure. This K-ARFT foundation enables new storage options, such as the diskless topics architecture, which allows brokers to serve segment files directly from cloud object storage. It also enables the upcoming Queues for Kafka update, which breaks the strict single consumer per partition limit to allow true parallel message processing. Whether managing local clusters or operating in the cloud, tuning for zero data loss requires mastering the physical constraints of disk segments, complex hashing algorithms, and raft consensus mechanics. Kafka's status as the industry standard stems from its uncompromising optimization of a single data structure, the commit log.